Hello. I guess my first question would be, can you see and hear us? Please write in the comments. Yes, thank you, Patrick. Okay, so terrific, and thank you, Mark. Okay, it's always confusing with these things. So my name is Eli Ben Sasson. I'm CEO at StarkWare, and welcome everyone to another Stark at Home episode. We have here Ulrich Habok, an applied cryptographer from Polygon Labs, Shachar Papini, and Andrew Milson from StarkWare. And today we're going to discuss Circle Stark and Stwo. So I'll give a brief introduction and then hand it. The schedule is going to be like this. We'll start with a very brief introduction. We'll hand it over to see some performance metrics and why at least we are very excited about what's coming. And then we'll talk first a little bit gently about like the math and innovation in there. And then time permitting, we'll go deeper and deeper into the math as much as you have patience for that. I urge you all to post questions. You can use the, I think you can use the comments for it. So like here's a question, and from time to time we will try to answer them. So, about 4 years ago, we came out with our first production system, and it was serviced by a prover that we call Stone. This prover was used to settle over $1 trillion worth of volume on top of Ethereum and settle hundreds of millions of transactions. And it's been working pretty nicely for the past 4 years or more in production. And it is open source now, and it works very well. But now we're actually building a new open source prover called Stwo. And its development is being done open source. We can share with you the link. And it's going to be much, much better and much faster. And to explain what we mean by much better and much faster, I'm going to hand it over to Andrew Milson to share some numbers. And again, after that, after discussing the performance and also offering some interesting research and collaboration avenues, we're going to try and explain why is it a little bit faster. So please, Andrew, take us through it.
Awesome. Well, thanks, Ellie, and hey, everyone. So yeah, what I'd like to speak about right now is a couple of things. I want to talk about the high-level design of Stwo, how we've gone about designing it so that it's fast on multiple different architectures and different kinds of hardware. And then I want to talk about the performance compared to Stone. And at the end, I'd like to talk about some exciting directions or some exciting things that we can collectively build as a community with Stwo. So yeah, let me just share my screen actually. Okay. So can everyone see that? Can everyone see my screen? So good.
I can answer, but yeah, let's wait for the people from the audience.
Yeah, the audience seems to see the screen.
Okay, cool. So yeah, so I want to start with the high-level design of Stwo. So our goal is to make Stwo as fast as possible. And to do that, what we've done is we've written the protocol in Rust, and then we've made it generic over a backend. And a backend is a type, but it's kind of two things. It defines how it stores its data, and how it operates on that data. And we currently in Stwo, we have two backends. We originally wrote the protocol and we created a CPU backend, which was kind of like our naive implementation, where we wrote the backend without trying to make it optimized for any specific kind of architectures or hardware. And that was good. We already saw like a really great performance. We saw a great performance increase over Stone from that alone. But then we created another backend, and we created a SIMD backend. And for those who may not be familiar with SIMD, it stands for single instruction, multiple data. And it's a class of instructions on the machine that instead of targeting one piece of data, target multiple. So an example would be you have an instruction that performs an addition on two numbers, and with SIMD, you can perform an addition on like 16 numbers in more or less the same amount of time. So when you utilize something like SIMD on a machine, you can get a really great performance increase. So yeah, so we built this SIMD backend, and we saw a really great performance increase on that. So yeah, that's a little bit about the high-level design of Stwo. It's we wrote the protocol, and then you can plug in kind of whatever backend you want, whatever hardware you want to support. And now I'd like to talk about the performance.
I just like to add that we do expect other backends to also be implemented for all kinds of hardwares like GPUs, FPGAs, wherever you want to, basically.
Absolutely. So I don't have the data on how fast it takes, how fast you can prove Cairo in Stwo. We're still working on that. But what I have here is just the single thread FFT performance of Stwo with both of our backends compared to Stone. So the blue line here at the bottom is Stone, and all of the dots at the top here is Stwo. And you're gonna have to believe me that the FFT is a big bottleneck for the prover. Like if you squint hard enough at the protocol, it's just a bunch of FFTs and hashes and polynomial evaluation. So by improving the performance of FFTs and some of the other primitives, it like directly translates to performance improvements of the entire protocol. So this is so I just want to say a couple other things about this. These red and pink dots at the bottom, this is the CPU backend I just talked about. And all of the, like the green, the orange, the purple, and the brown, like these are all the SIMD backends. And was actually something that maybe the engineers will find interesting is like we originally wrote a backend for AVX 512 specifically. We just focused on AVX 512 instructions. And then we switched it out with Rust's portable SIMD library, and we saw no degradation in performance. And what we got along with that was not only like a implementation for AVX 512 SIMD instructions on Intel machines, but we also got like really good performance for AVX2 and even WebAssembly and the Neon instructions on like an M1 Max. And like the difference between like the M1 Max performance, the native performance with Neon instructions and WebAssembly, there's only like a 30% loss when in WebAssembly. I thought that was quite interesting. And also if the log scale doesn't make it clear, like the difference between the Stone FFT performance and the Stwo FFT performance is like 200x. So it's a real jump in performance. And this is just implementation of an FFT, but in Stwo, we haven't just optimized the implementation. We've also we're using more optimal algorithms. So so Shah will touch on how we're using GKR for things like lookups and mixed degree to get improved performance there. Okay, so that's the that's a little bit about the performance. And yeah, the other thing I just want to say is that the backends are modular. You can create your own backend in your own repository and plug it directly into Stwo. And if anyone's excited about this, I think it would just be so awesome to have more backends, as kind of Shah mentioned. So like the backends can define how they store memory and operate on that. So anything from like an NVIDIA GPU or some crypto specific hardware like a Fabric VPU, or even really fast implementations in the browser using WebGPU can all be supported in Stwo, and people can create their own backends for this. And I think that's really exciting. Like we'll see more orders of magnitude performance on top of the SIMD backend. I think if we see these backends, so I encourage anyone who's interested in that to explore that, and yeah, feel free to send a message about that or anything like that. So yeah, anything you'd want to add, Ellie, Shaha, or Ulrich?
Well, do you see the question? Maybe there's a question by Patrick Grinaway that Shah already answered, but maybe you can answer it for the audience. How should we interpret the throughput of the FFT? Does this directly translate to the performance of the LDE step? Patrick.
Yeah, exactly. So the throughput here is like elements, like field elements per second. So in terms of Stwo, this is the Mersenne field, and in terms of Stone, it's the field used with Cairo. But yeah, so that's kind of how I'm looking at throughput. But for instance, like let's take Cairo for example. You'll have like an LDE over the addresses used in Cairo, which could be stored in a Mersenne element. So you can actually, although the field sizes are different, you don't need a large field to store a lot of the things that you need in like an air for a VM or something like that. So yeah, I just want to mention like the throughput is for field elements, Mersenne versus the Cairo field.
Okay.
Yes. I want to emphasize that the 200x you see here is, again, for field elements, and it really depends on the statement you're trying to prove. Like some statements, if you go to smaller field, you don't need to add more of these field elements. In some, you do. So it depends on the statement you're trying to prove. But like Andrew said, usually in VMs, then you get this 200x trade-off because you usually are not using big values in your elements. Yeah.
I have a question, Shaha, because I don't have any clue of neither implementation of yours. So the Stormprover, that's in Rust?
It's C++.
It's C++ even, okay. And it uses also SIMD?
Well, it's a good question. Using SIMD did not provide the performance gains because we are using another feature of the CPU, specifically of Intel CPUs for these multiplications. It's not vectorized, but it is using like a more efficient version for the multiplication and propagate carry. It's like a CMUL, a CAD, something like that. So for the big fields, we did implement it as performant as we could. Using vectorization did not make it more performant in that case.
Really? Okay. I'm not a developer. I'm quite surprised. I mean, couldn't you just scale, say, across columns? That means row-wise. You do always the same operation, even if it's large.
But you don't have the same operations in vectorization that you have on single elements. There are these operations on single elements that did more things than the just vectorized versions.
Okay. Thanks.
Sure.
Okay, so Andrew, are we done with the performance discussion?
Yeah, I'm happy to pass it over now.
Okay, so maybe let's move on to talking gently and lightly about some of the math. We saw here the FFT that I guess some of it is the effect of moving to a smaller field, and we'll talk about that a little bit later. But there are a number of other improvements that will go into Stwo. Most notably, two of them are the use of GKR and mixed degrees. So now I asked Shachar in advance to prepare a gentle, non-math explanation of what is each one of these and why should we care and how will they improve performance. So let's start with GKR. And I encourage the listeners, if things are not clear, please ask questions. And so Shachar, what is GKR? How should we think about it?
Yeah. Okay. First of all, Starks began in a really specific way. Starks have their pretty much, there's a table of values and you have some constraints on them, and that is what you prove. That is how it started. That's how Stone works, and that's fine. There are other proof systems which are not Starks, which use other kinds of mechanism instead of this constraint system that is proven using Starks. They use sum checks, things like other things, and the problem was that sum check needed some primitives that weren't in Starks. A bit more technical, Starks need univariate polynomials, and sum checks need multilinear polynomials. That is, polynomials with a lot of variables, but of degree 1 in each. And these things didn't really fit together. However, it turns out they can work together, and that is exactly what we are doing in Stwo. And I'll explain the benefits. Sum checks enable this GKR thing. It's a cool algorithm, it's a cool protocol, also for proving some computations. But instead, like in Stark, of taking your table of values and committing on it using some kind of a hashing it and sending it to as the proof, instead it's using multiple rounds between the prover and the verifier to prove the some kind of arithmetic circuit. If you have these inputs, you do some operation, all of them, you get some output. So it's trading off. Instead of committing to all these intermediate layers, it's doing more rounds of pulling randomness from the verifier and sending things from the prover. That is the trade of GKR. Sometimes it's okay to take, sometimes it's not. It seems like the best way is to combine both. We have a single error on some of the witness we are committing on, and some of the computations on this witness we're using GKR to prove. And we get this combination that makes our errors more efficient. Specifically, we took as an example proving the Blake hash. The Blake hash is a hardware hash. It's fast for hardware and for CPUs, but it's not as efficient to use in Stark proofs. But using both GKRs and regular Starks, we were able to cut down the cost of the proof about x2, x3, something like that. And that was enabled by this way to combine sum checks, GKR, and Starks. So that is one thing we have in Stwo. I think Andrew worked on implementing it, so maybe he can also provide some details on its concrete performance. Okay, that is one. Yeah, okay.
Yeah, how much does it save? Like this moving to more rounds of interaction, but fewer use of hashes.
So what we saw is that with grand products, I think it was a 2 times increase in improved performance. And I think we expected it to be faster initially, but the FFT, so previously we'd done lookups with FFTs and hashing, and those are so fast in Stwo that maybe we were expecting like a 5x or a 10x, but it was really only a 2x because in Stwo, FFT and hashing are just so fast anyway. With the lookup arguments, I think we see kind of more like a 3 or 4x improvement, and these translate to big performance improvements overall, because something like Blake 2 would have thousands of lookups.
So there's a question here. Is there any significant, again, Patrick, thanks for asking excellent questions. Is there any significant effect on prover memory usage with GKR?
Yeah, it's a good question. There is some kind of trade-off you can do there. Like if you do it naively, you still need to keep everything in memory. You can do some trade-off that for the intermediate values, you can keep only some of them in the memory at each point of time, but then you pay with more rounds or more overhead later. So if your main concern is memory, you can use this to reduce the memory. But again, it's a trade-off.
But aren't they all of them like sort of O of n anyways? Like,
but it depends on, like, if you're bounded by the maximum memory, then you don't want to keep all of it together. Let's say you have your witness is of size 100, but your intermediate computations are of size 400. So instead of saving 500 in memory, you could maybe reduce it to like 200 at most, and do it and splitting the 400 intermediates to 4 parts, each one of size 100. You can do things like that. Okay.
Ulrich.
Yeah.
Which hash are you using?
The hash we are using Blake hashes for the prover as well. We are proving the statement of Blake's, and the proof itself also uses the Blake hash for the commitment. That is to allow us to do recursive proofs. The reason we chose,
I'll ask, isn't it a trade-off where it's very efficient in terms of CPU to hash, but then very inefficient to recursively proof that you use the Blake?
It is, but okay, if your main concern is to reduce the overall prover time, and you assume that you have enough things to prove, then you can always, because the verification is sublinear, you can always take computations which are so big that make the recursion insignificant anyway, even if it costs 2x or 3x. So it still pays off if your intention is to reduce the overall cost of proving. You want to make the prover as fast as possible. And another point is, assuming you are doing recursion, at the end, at the last proof, you can't start to do like recursive proofs that are more beneficial for the verifier to make the final proof very verifier efficient. So you can somehow enjoy both worlds.
Okay. There's another question now. A lot of very good. Oops, sorry.
Can I run into here, because I was trying to answer one of the questions. Hope I did it. So where are places where GKR is a benefit versus a classical univariate strategy? That's typically, I mean, the main benefit, as Shachar was pointing out, is or let's say the trade-off you face here is, on the one hand, a multi-round protocol with this many interactions, but intermediate results are not committed, so no hash of intermediate states, versus something, an univariate strategy that that computes all where you commit all the intermediate states and use universal strategies to prove it. So in particular, it's the cost of the GKR protocol itself, which uses a lot of linear extrapolation steps. That's the linear and multilinear protocol. That costs a lot because it do it over large domains. And but you don't commit. And in the end, it's about really, first of all, which hash function do you use? Is it something like Poseidon, which is more costly and primitive? Or is it something like Blake, which is very fast and primitive, but more costly than Poseidon in circuit? Things like this, versus how fast is the arithmetic steps you do in every single round of the GKR protocol.
So there's another question here. Does the Logan, by the way, terrific questions, keep them coming. Does the fact that GKR is an interactive protocol lead to a downturn in performance in memory?
The interaction is first a verifier penalty. And the verifier needs to do a lot more hashes in its verification for each round, basically. So that's the first drawback. In terms of performance memory, the performance is actually better assuming your computation is in the extension field. It's a bit of like a fine point. If the computations are in the base field, then there's still stuff you can do. It's like at the edge of research. We don't have any of that yet in Stwo, but when it's computation in the extension field, then like Andrew mentioned, the performance is better. The memory naively isn't better, but you can do another trade-off that makes the memory a bit better, and you again pay more for the verifier and a bit more for the prover. So you have like two trade-off space you can do with GKR, which generally gives better results.
I want to add here that I think this was mentioned before, but like the use of GKR, like GKR or some checks are very useful when, and also Ulrich wrote this, when what you're verifying with them or proving with them is a very shallow and very wide circuit. So in the extreme case, if it's something like a lookup table where basically it's like depth 1, because the complexity grows with the depth of the circuit or the computation being made. So probably for general purpose sequential computation, GKR doesn't work as well as using AIRS, but for things like lookup arguments or logup arguments and very, very shallow circuits, they work very well.
Right.
Okay, let's see if this, I remember it was claimed 1.6x speed up in the paper for some memory issues. What is the obstacle for the claimed 100x speed up in Stwo? Is that solved? I'm not sure I understand exactly the question. Maybe you guys understand.
Do you mean, like, it seems like you're mixing memory with the runtime performance?
No, I think the 1.6 I think was over in the white paper. I think there's a comparison of Circle STARK to some other small field like Baby Bear. And here we're talking about Stone, which is over a much larger field. So yeah, exactly. Right. Oh, sorry. So the 1.6 in the paper is compared to
Baby Bear, right?
Baby Bear, which is another 32-bit prime or 31-bit prime. Okay, so let's move on to the next improvement, which is what do you mean by mixed degree? What give us some informal explanation of what's going on.
It's not something that hasn't been done before. Some people did it. I think even Polygon had some version of it. But basically it means, remember I said in Starks we have usually this table of values. Well, sometimes you can't really fit your statement in like this rectangular table of age on W. Sometimes you have like columns of different length you want. For example, maybe I'm doing like 1,000 hashes, but only 200 multiplications or something like that. I want things to not be of the same degree, not all the columns to be of the same length. So what we can do and what we do in Stwo is basically have multiple, it's sort of like multiple tables like of different heights, but we're not committing on them separately. We're committing on them together using Merkle tree shenanigans and Fry shenanigans by Fry, for example, is a protocol that based on layers. You have this big layer, and then you fold it to a smaller layer, big layer, smaller layer, and then you fold it to a small layer. So you can imagine that if I start with a layer of size, let's say 1,000, and then next layer is size 500, then I can here jump and add another column that is shorter. If I had like a column size 1,000 and another column size 500, I can add it later in the Fry protocol or later in the Merkle tree. So that is what mixed degree means. That it gives us better packing of the data we want inside the commitment we have. So we need to do less hashes and not waste this commitment space. And B, the degrees of all kinds of things like constraints and polynomials and Fry, these degrees can be lower than they would have been before. And that actually affects the performance directly, because for a constraint, you need to do some work for it in Stark. This work is proportional to the total degree of the constraint. So if you have a constraint that work on smaller degree polynomials and the total degree of them is smaller, then you work less for them. Yeah, this is a mixed degree, basically. Let's see. Are there any questions? Is there a soundness consequence for mixed degree Fry? Not that I know of. Yeah, Ulrich Hensel.
It's negligible. It's negligible. You know, if you look carefully at the formula from the proximity gaps paper for batch Fry, because it's always, it's always about the random linear combinations, either the big, the huge batch in the very beginning, or the smaller batches of just odd and even functions in the folding cascade of Fry. But essentially, there is an influence on the size of the batch. So how many functions are subject to the linear combination or on the soundness error, but it's negligible. Yeah, maybe 1 bit, 2 bits, something like this, 2 bits of security. So typically something which is not of concern.
Yeah, I'll say that when it comes to soundness, for mysterious reasons, up to the fact that, that's like what just the math shows, there are certain parts that are very, very good soundness, like the linear mixing of various commitments. You pay pretty much the minimum possible that you could hope for. So if you add k things, you select randomness over a field of size q, then your soundness, you lose something like k over q, which is very, very negligible, because often k is small, let's say less than 1,000, and q is like by this stage really large, like 2 to the 128 or maybe even larger. So you lose a very small soundness. There are things where you lose in a much worse way, which is more correlated to the rate of the polynomial or the blow-up factor, and that is related to the queries. And there, it's actually soundness isn't as good. It is the ratio between, either the ratio or square root of the ratio between the code length and the and the degree of the polynomials, and that's like a very major. Things are not as good there. But luckily, the mixing or mixed degrees is on the part where it costs you almost nothing, as Ulrich said. There's another question. Logan is asking, are there constraints between the subtables with polynomials of different degree?
Yeah, that is also a good question. You can do them. We try to avoid them. The reason is it adds inefficiencies. Let's say you have a constraint between a column of size 100 and one of size 500. Then you need the total degree of the constraint would be 500 because it has this polynomial of degree 500 in it. So you would have to evaluate it on 500 points in the STARK protocol, and that means that the small column of only size 100, you have to evaluate it in a lot of points all of a sudden. So it adds these kinds of inefficiencies. Sometimes we have to do it, but usually we try to avoid it, and we link different size tables using lookups. And this is more efficient usually.
So did we measure Circle Stark performance for other fields? I mean, I know the short answer is no, because we didn't, it's not that easy to implement efficiently, any sort of FFT. So the answer is no.
Yeah, we haven't.
Okay. By the way, but also even like M127 would still be it's like half the size of the stone prime. So you'd expect it to be a bit M17 more interesting. All of these are Mersenne primes. There's so many of them. Okay. Okay. So let's move on to the to a third part of Circle Starks. I'll try to give an explanation of something that I actually wrote in a blog post. So you're welcome to. I put it here in a comment. You're welcome to read it later and share with your friends. And it is so I attempted to explain like why am I excited about Circle Starks and what is even going on. So let me try and run this explanation, this very informal explanation by you. So one part that is obvious and I think is a major part of the explanation for the 200x improvement from moving from stone to Stwo is just that you get to work with smaller size numbers, right? So the stone system works over 252-bit numbers, and now you sort of, each multiplication and addition takes many cycles. We counted around 40 cycles to do one multiplication. And when you move to these 32-bit integers, especially, well, not all 32-bit integers apparently behave the same when it comes to things like multiplication and addition. And the reason for that has to do with a binary representation of them. And in this case, Mersenne primes are very special, not just because they're named after Mersenne, but because, well, think of M31. It is the prime 2 to the 31 minus 1. So if you're working modulo this prime, which is what you do when you work in this finite field, it means that the number 2 to the 31 is equal to 1. So 1 with a lot of zeros, I guess 30 zeros or something, or 31 zeros, is equivalent to 1, which means that when you're doing modulo operations and reductions after you did the multiplications or additions, you get something that is very efficient and involves a very small number of cyclic shifts. So not all 32-bit primes are the same, and you would like ideally to work with something that is like a Mersenne prime. It would be really great. However, there's another thing that you want from the modulus that you're working with, and this has to do with the structure of groups over this finite field. So I'm assuming that if you stayed with us so long, you probably are not afraid from hearing the term FFT, the fast Fourier transform. And I'm guessing that a lot of you probably remember learning the FFT algorithm or reading it someplace. It's this beautiful, super efficient algorithm that basically moves from one representation of a signal to another. And when you heard about it first, you probably were given a signal transformed by evaluating it over roots of unity, and the number of roots of unity was a power of 2. And the reason you want an exact power of 2 is because you have this beautiful recursive structure. If you look at the number, let's say 2 to the 10, if you divide it by 2, you get another number that is of the same form but smaller. It's 2 to the 9. You divide it again by 2, you get 2 to the 8, and you can repeat this time and again. And if you remember how the FFT works, you take a sequence of size n, and you break it into 2 subproblems of size n over 2. And if you want to repeat this thing time and again, so you want to take something of size n, break it into 2 subproblems of size n over 2. Well, for that to happen, you want n to be even. But you want to do this again. So you want each one of these n over 2 chunks, you want to be able to break them up into 2 even parts, 2 equal size parts of size n over 4. So you want 4 to divide n, and then you want 8 to divide n. And it's not hard to see that you would like a number of points, evaluation points, that is an exact power of 2. And really, I think pretty much all FFTs, really fast FFTs that are used in the industry for signal processing or learning or whatever it is used for, they will take signals of size 2 to the n. Well, it turns out that when you do our low degree extensions, you want a similar structure. You would very much like a number of points to evaluate your functions over that is an exact power of 2. So you can do like things like FFT, and it even shows up in things like Fry, this sort of breaking up into 2 chunks of even size. The problem is that the Mersenne prime doesn't have a set of points that both form a group, and the size of this group or the number of points on it is an exact power of 2. And the reason for that is that the multiplicative group of Mersenne prime is actually 2 to the 31 minus 2, which if you factor it, it's 2 times some odd number. So and because of this, you won't have a group. You're very far from having a group of the right FFT structure. Okay, now this problem was already tackled previously in the context of Stark's in this mathematical paper about using elliptic curves. And the key idea was to say, well, we really want a group of size 2 to the k that is defined over the field. And we would like it to be an algebraic group. So the brilliant 3 co-authors of the Circle STARK paper said, aha, there is a very elegant algebraic structure called the circle, which is defined by the equation x squared plus y squared minus 1. So it's the good old circle that we all know from high school, elementary. And it turns out that the points on the circle defined over the Mersenne prime, the number of points there is a very high power of 2. Forgot if it's 2 to the 30 or 2 to the 31. And more, so you have like this structure that is a group and is of the right size and is defined over the this Mersenne prime that allows you to have fast arithmetic. So if you want to read more about this or explain this to your friends, because I'm assuming that a lot of our listeners actually understand this and didn't need my explanation, you can go and point them to this blog that I wrote about it. But now, unless you have questions about this explanation, I'll hand it over to Ulrich So first of all, I'll ask, do you have questions about what I said? And if not, I'll hand it over to Ulrich to give a little bit more mathematical rigor into what is Circle Stark and why should we care. So Konstantin is asking something in Russian, I think, but I don't. So if someone can translate it.
The first word is super, no? Super, and then no
Ruski. Okay, sorry.
Yeah.
Okay, well, if someone can translate it, we can try to answer. But do extension? Well, I guess what exactly do you mean by do extension fields? First of all, the circle. Okay, the circle, just like if you look at x squared plus y squared minus 1, right? It has a bunch of solutions over the integers. I think it has 4 solutions, right? 0, 1, 1, 0, minus 1, 0, and minus, well, whatever, right? The 4 points. It has an infinite number of solutions over the field of rational numbers, and has many, many more solutions over the reals, and even more, well, the same, how do you say, the same cardinality, but a lot more solutions over the complex numbers. What am I saying? As you move from one field, right, from the, as you move from the field of rational numbers to real numbers to complex numbers, you get more solutions. And the same thing happens, of course, with Circle Stark. So as you go from Mersenne to some finite extension of Mersenne to the algebraic closure, you'll have many, many more solutions, and also a beautiful group structure. So yes, and maybe it will even come in handy one day. Yeah, good question.
Yeah, actually, we just one off to the case we used. No, I mean, with classical univariate Starks, the line, how many points does it have? As many points as the field is large. So that's the size of the field, right? I'm trying to.
Okay, I assume. Yeah,
do something also in the chat here. So, and if you take
another good question.
Extension, that's exactly what you were targeting at, no? If you take, let's say, an extension field of degree E, that's, wait, I'm typing it. So then you just have like the E's power of that field. So that's what you're used to. And with the circle, it's quite similar. It's just that instead of F, the size of F, it's always the size of the field plus 1. So we're just one off, but the same, like if we go from, so the Mersenne M31 has 2 to the 31 minus 1 points. The circle has 1 point more as the field is large. That is exactly 2 to the 31. If you have a quadratic extension of it with quadratically many points, in short, then the circle over that extension has the same size of the quadratic extension plus 1. So essentially the same behavior. So it means for security, if you're used to scale up to degree 4, degree 5 extension or beyond, depending on the base field, the same blow up from small field to soundness field you face with the Circle Stark.
So there's another question that I can try to answer. I assume you need a larger field than 31-bit for soundness. It was curious how this is accomplished. So you're right that it goes like this. For the basic arithmetization, if you take your computation and write down its trace, the only, you need your field to be just as, for perfect soundness, you just need your field to be just, as large as the size of the computation. For later interactive steps, you're right that you need to sample randomness from a large enough field, because part of your error, as we said before, like when you do like batching, so you pay roughly, well, the number of batch things, if it's k, your soundness error is going to be like k over the size of the field. So you do need a larger field at that point. And yes, you can then move to the proper extension field. Like in this case, it would be the degree 4 extension. You'd have 124 bits, which is probably good enough. And the nice thing is that all the steps before that, where you do arithmetization and FFTs, those parts you can do over the base fields and not have this extra factor. Great question. By the way, terrific questions. In the paper, it states that FFT will be the same as radix 2 with different twiddle. Can you provide a little more details of this? I mean, the butterfly diagram would look the same as radix 2.
Yes, I tried to answer in the comments. Yes, it looks exactly the same network, just with different values. I also sent the link to the implementation if you want to look, but it's just radix 2 FFT.
So I guess the answer to this is yes, right? For Circle Stark, you need projective space and add complex number. I guess yes. And then, well, last one, which this is about speculation. How does Stwo impact gas fee? I'm sure it's going to do a lot of wonders. Like right now on StarkNet, like gas fee is very, very low already. Like whatever, sub a cent for. So probably would bring it down, I don't know, by a factor 100. I'm guessing, I don't know. We're still very far from knowing the exact effect of it, but won't make things worse. This is interesting, but I you know, we're in math. Yeah, sorry, dude. I mean, I feel for you. But this is for math discussions. Okay, so Ulrich, all yours. Can you walk us through just a little bit of like what is the math of Circle Stark?
Yes. So actually, in a nutshell, the Circle Stark is a simpler construction than the ECFFT or the elliptic curve Stark that Eli mentioned before. So you know, ECFFT Stark, 2 papers, about 70, 80 pages each, a lot of algebraic geometry because elliptic curves. Of course, everybody works with elliptic curves, even developers, you know, or applied people like me, but really deep understanding of the theory behind it and why do they look so, at least I don't have it. So that's main benefit one is the entire construction that was done with the ECFFT and the ECFFT Stark. We just took it over to something that is so easy to understand. It's the circle, and moreover, because the circle has such a simple structure, you can take this even as an occasion to learn or to approach algebraic geometry if you like to. You don't have to; it's not necessary. But I learned basic notions of algebraic geometry by it, and yeah, with this with having this simple structure, I think the paper is much more readable. But to be clear in it, so if it comes to performance, there is no benefit. You could run M31 elliptic curve Starks. It would be essentially the same in speed versus the Circle Stark. But the Circle Stark is much easier to implement, much easier to understand, much easier to audit and things like this. So, and the reason why it's so much simpler is that the group, I mean, every FFT is related to certain symmetry groups that like a rotation group as we used in the classical FFT, and the same holds also for the circle. So if a group that that is not that complicated as in the ECFFT. So let's say if I just drop some names here, and it's probably going too far, it's an affine group. Consequently, the objects you encode witness data into, what's in an univariate Stark? It's polynomials. You place your values over the trace domain, and you encode it into polynomials as we used to. Over the ECFFT, you end up with rational functions. Still algebraic of low degree, but rational functions, it's a bit more harder to understand them. Or with Circle, again, you end up with polynomials. These polynomials, they're polynomials over the circuit, means they're in 2 variables. That's the only difference. And actually, because of x squared plus y squared is equal to 1, that's the circle identity. Because of that, you can even replace every quadratic power of y with a quadratic power in x. And if you do this repeatedly, you can boil down the powers. You can kill out all the high powers of y, ending up just with a linear power in y. That's already going too much into details. Let me rewind here and let's close Pandora's box. So it's a much simpler construction than the ECFFT. We end up encoding again in polynomials, and as a consequence, we can take very much directly over from the intuition we gained from the univariate Starks as we know them to the Circle Stark. That's in short the big advantage of it. I think we're already running out of time now.
Questions?
Oh, that's bad. So I talked too much.
No.
No questions is never good.
Maybe everyone understood everything, but let's see. I'll ask a question. I mean, so we now know that you can use, like, let's say, groups of elliptic. Okay.
There's a question.
Exactly.
More.
Exactly the question I wanted to ask. So I'll just say it in more words, because we know that. Thank you, Yao. So we know that you can use the group of the elliptic curve to do some stuff, and now we know that you can use circles, which are genus 0 curves. There are so many algebraic curves defined over fields. What is, will we see more?
That's a good question. As
I can try to answer.
Let me give you first my view, and you have probably the deeper answer here, really. But just from the way of applied crypto, or let's say from the implementation perspective, as I know from our team at Polygon, it's like, because I was always asking, M17, is that of use? Because there's many traces which make sense just to go up to 17, look up arguments for 16-bit range proofs. That's exactly, it seems to be like kind of sweet spot from the view, from the mathematical point of view. Nevertheless, on standard CPU architectures, they're all set through it throughout. No, you really don't gain any performance advantage here anymore. So that's one thing. So I would guess there is already the ECFFT. In terms of performance, I wouldn't see any improvement with any other type of group here than the classical FFT as we know it, like being log linear, to be short. Yeah, Eli, better.
Yeah, I have another answer. So there's a story with it, because so years before, this was before StarkWare. So I was doing a lot of research on proofs of various sorts, and there's this let's call it one round IOP, which is called a PCP. And there are many terrific questions about PCPs, and one of them is has to do, can you get like PCPs with very good parameters and also defined over a constant size field, like whatever, 5-bit field, even if your computation size is really large. And so we realized, this was probably more than 10 years ago, that there's a way it can be done, but only if you use these very exotic algebraic groups that are formed from towers of fields and stuff that I completely don't understand. And all of my co-authors didn't understand either, but we knew who to ask. Like, we needed these very weird exotic structures. We needed the groups that are transitive and over small alphabet, and like over these asymptotically good codes. So we wrote to Henning Stichtenhoff, who was one of the leading, still is one of the leading authorities on these algebraic geometry codes. And we were expecting him to answer either yes, and here's a result, or to say no, and it's probably a deep open problem. But he wrote back to us, like after we asked this question, he wrote back and said, oh, you know, I know how to do it, but I never bothered to write it down. And we were like, really, man? I mean, this is like really important result. You should write it down. He said, well, you know, I didn't, whatever. I didn't have the time or something. So we ended up having this paper that has an appendix by Henning Stichtenhoff that uses towers of algebraic, towers of these fields and curves over them that give you something of benefit. Like it allows you to use a very, very tiny group, very tiny field, and to have very short proofs. All this to say that, you know, math always surprises you and there's more to do. And I'm sure that more algebraic groups and structures are going to be used for like a lot of beautiful things. If I had to guess about one particular thing that may be of interest, like right now we're dealing a lot with very sequential computations. And for that, all you need is like a cyclic group. And maybe there, like between the finite field, you know, a circle and an elliptic curve, you're done. But if you want things that are like massively parallelizable, then maybe you want like some other group that is much more, not cyclic, but has a few different generators. And then you're going to need to dig deeper into algebraic groups. Okay, we definitely went, I think, on a deep tangent. Who wants to? So each one of you, please summarize. Why are you excited by Circle STARK? Who wants to go first? We'll go backwards. So Ulrich, then Shachar, then Andrew. I already said why I'm excited.
Yes. So why excited? Because I mean, mainly we at Polygon, as a lack of our understanding of the ECFFT back then, we tried for simple approaches. For the M31, Daniel Lugarov was very much pushing from early days. I joined. We need to move on to smaller fields like M31, and that this little draft, this write-up we did, these simpler constructions, we were very enthusiastic in the beginning, and then we discovered, okay, there are some caveats, and the caveats are like when it comes to constraint evaluation, in short. So beside it, and the FFT is not as fast as the CircleFFT. So CircleFFT, and working together with Shachar here and David, that was like super exciting for me personally, because it knew, first of all, I could learn algebraic geometry. Second, I could tell Daniel M31 is the way to go for us, at least midterm. And third one I forgot, but for sure I forgot because I'm too excited.
Okay, my turn.
Yeah.
No, I think Circle STARK and Stwo will open up so many possibilities with this. It's great performance, and not just scaling StarkNet or it's open source. So every project that ever needs to prove something will have a fast prover, and will come up with these crazy ideas to how to use ZK technology for them. Open up a client-side proving, which will be very efficient. To just open up so many things that we can't even imagine right now. That's how I see it.
Andrew.
Yeah, I guess I'm excited because it seems that like Mersenne Prime seems to be like the most optimal for CPUs, GPUs, at least. And I just think that, yeah, the kind of performance we'll get will just be insane. And that's very exciting. It's also just cool stuff. Like for me, I think a lot of the math related to it is new, and it's exciting and fun to learn about. Like there's something magical about it. I don't know. So yeah, I'm pretty excited. And,
yeah, I'll say that I'm so happy that we're moving to small fields of any kind. I mean, when like the original ZK Stark white paper was over a 64-bit field and even a binary one. And I guess I have this obsession with small fields because they're just so efficient. We can talk some other time about why it was definitely the right choice to start with a simpler, very large prime field for Stone. But I'm really happy that the performance demands and basically our collective understanding of how to build really efficient Stark provers allows us now to use much more efficient and smaller fields. They're just so fast and efficient. So that's why I'm really excited about it. And also like the beauty of like this integration of math and engineering is just so powerful, and it's just so fucking amazing that we take these amazing, high-level math things and then bring it into code that is just used massively, is going to be used massively by humanity. It's just mind-blowing, and it's like such a beautiful thing for cryptography, science, and math to be done in this way. I'm just so happy to be observing it. Okay. Thank you, everyone. Hope to see you again on another Stark at Home. And take care.
Awesome. Thanks, everyone.
Bye.
Yeah.
Thanks for having me.
Thanks for joining.
Bye.
Bye.